first we're going to start off with, does a compass point to the geographic North Pole of the Earth? Why or why not? So, when we were little kids, and not trying to just point out Christianity here, people, we learned that Santa and the penguins come from the North Pole because Santa flies on his sleigh. Well, I hate to break it to you, people, but penguins also come from the South Pole. You know, it's a sad truth that we all have to learn one of these days. But penguins do come from the South Pole. And yes, our compass does point to the geographic North Pole. But what we're about to learn is opposites like to attract. And many of you are like, well, if it's opposite, then why does north attract to north and south attract to south? Well, sweet peas, I'm going to blow your mind, because technically the geographic North Pole is technically the magnetic South Pole. And then the South Pole is the magnetic North. Because then when we kind of go back to the idea that opposites attract, our North Pole, our north pointing cointus, oh, it's a compass. Our north pointing compass points to our magnetic South Pole. Yeah, right? Yeah, that makes sense. Perfect sense. And then our south pointing compass is attracted to our magnetic North Pole. Mind-blowing, people, mind-blowing. Okay, so we're going to talk about the shape of a magnetic field around a current-carrying conductor and how to determine the direction of the field. And we're going to do this by using the first right-hand rule. Well, to use the right-hand rule, we're going to need a right hand. So, here's a hand, and we're going to need a current-carrying conductor, which will be this blue expo marker. Now, to determine the direction of the magnetic field around the blue expo marker, we're going to curl our fingers around it. And that's going to be the direction of the magnetic field around the current-carrying conductor. So let's draw that on our single line here, going counterclockwise, just real quick. And let's just talk about the direction of the current while we're talking about this first right-hand rule. So when we have our fingers wrapped around the current carrying conductor, the direction of the current in the conductor is determined by the direction of our thumb. So right now, our current is going up. So let's just draw that here. And the symbol for current is I. So there we go. Next, we're going to draw our magnetic field around our conductor using some symbols. So, we're going to draw some little dots on one side to symbolize that the field is going toward us, and that we're going to draw little X's to correlate with these, saying that it's going into the paper or away from us. So it still has this counterclockwise motion. We're just going out of the paper. Ooh, as I screw up my drawing. And into the paper. And that's it. That's all you need to know for the first right-hand rule. Okay, next we're going to talk about what is a solenoid, what is the shape, and the direction of the magnetic field around a solenoid. So when I think of like a solenoid, I like to think of a kind of a spring or coil that just loop-de-loop all the way around. But the special thing about a solenoid is it has current flowing through it. It's just a curled wire, basically. And so to determine the shape and direction of the magnetic field, we're going to use our second right-hand rule. And so for our second right-hand rule, I'm going to need another right hand again. So, right hand swag. And I don't have a coil with me, but I do have a very chubby expo marker, so this is going to have to work. So when we're talking about a solenoid, we're going to still talk about kind of our first right-hand rule. So when we curl our fingers around it, this is now going to be the direction of our current in the... Oh, excuse me. This is going to be the direction of our current of the solenoid. The inside of the solenoid, the very inside or the tip of the expo marker, is going to be where our magnetic field is. And we're going to quickly draw that out, just very quickly. So with my artistic skills here, we're just going to draw a simple circle, and then we're going to have two ends coming out. This is our side view of our solenoid. So what I'm saying is when we're gripping it like this, and I'm going to say that the current is going in a counterclockwise direction still. So this is our current. And then I'm going to say that our magnetic field is in the middle, going out on both ends. So the magnetic field would still be coming out and around and following the same idea as a magnet going from north to south. So I hope that makes sense. Okay, so finally our last right-hand rule is our FBI rule. Force stands for, well, F stands for force, B stands for magnetic field, and I stands for current. So we're going to do our right hand one last time. Right hand swag. So as I said before, when we're talking about a current carrying conductor, our fingers wrap around it to create our B, or our magnetic field. Our I is our thumb, and our F is going to be our palm, which is going to be parallel to our current. And it comes out of either side, depending on which way the current flows. But y'all are probably wondering, well, how does this relate to an electric motor? Well, an electric motor turns electrical energy into rotational kinetic energy. It's based on the torque exerted by a magnetic field on a loop of current in a field. Whew, that's a mouthful if I've ever heard one. So let me show you a little picture from this review packet I got. So when we look at it, this is our current carrying conductor, and it's obviously going in a counterclockwise. It's connected to a battery, so it is a closed loop. And these are our two magnets. And it's spinning from the electrical energy, which is creating the torque that we need to start our mower. Or your car, whatever you want to say. Okay, we are going to talk about 3 different types of magnets. The first type of magnet we're going to talk about is a bar magnet. Now, when we talk about a magnet, every magnet has a north pole and every magnet has a south pole. It doesn't matter if you break the magnet apart or anything, because it's going to repolarize itself to have a north and south pole. You cannot have a magnet without a north and south pole. You can have a magnetic attractable, which is attracted to a certain side of the magnet, which gets polarized by it, but you can never have a magnet with just a north or just a south. So let's dive in. When we talk about a magnet, we always talk about having magnetic field lines or flux lines, which determine the density and strength of the magnetic field. Now, these flux lines always flow from north to south, and they never cross, which is a huge major key. Ha ha ha. Hint to DJ Khaled there. But the cool thing about these magnetic field lines is they actually go through the magnet. So it's technically a closed loop system, and they just keep flowing forever and ever, which is kind of cool too. Our next type of magnet we're going to talk about is magnets with opposite polarities that are near each other. Again, we're talking about the shape that the magnetic fields make. Again, I'm going to emphasize this point. Magnetic field lines flow from north to south. So this is actually going to go across, and it's going to go around to the other side. We can't always forget our other pole. So no matter what happens, we're going to go up and around and up and around. And again, they do not cross. They can get very close to determine the strength, but they do not cross at all. Okay, so the next type of magnetic field lines we're going to draw today are our opposite poles. Woo, that's a mouthful. So basically we're going to have two magnets that are near each other that are north and south, or south and north, whatever you want to say. And we're going to just draw some magnetic field lines for that. So we're first going to go from our north and south. Yes, they are going to go across, which sounds kind of weird. But we also have to remember our other poles too. So we're going to draw all the way around and complete a loop. Even though this doesn't complete a loop, we're still going to complete a loop just to balance everything else out. And that is how we draw magnetic field lines for opposite poles. So the final type of magnetic field lines we're going to draw today are our like poles. So in this case we have two north poles. In other cases you can have two south poles. And that's about it because there's only north and south poles on a magnet. So let's get started. So when we talk about our north poles, they're obviously going to try to flow to their opposite side to their south poles because they're like, I miss you, I want to connect to you. And all that shebang. But when we talk about the two coming at each other, they're going to form this like awkward barrier where they get very close but they don't actually touch at all. They kind of repel each other because opposites repel and likes attract. So there's just going to be this like awkward space. It's like they're not liking each other. They're kind of like not friends. And they're keeping their distance from each other at all times. So that's how we draw magnetic field lines for like poles. Okay, so we are next not going to draw anything fun or have any more fun diagrams for the rest of the video. But stay tuned, because electromagnetic induction is very, very, very fun, especially when they relate to electrical generators. So electromagnetic induction is the changing in the magnetic field to create electrical fields. And it's actually kind of interesting how it relates to electrical generators, but let me go into more detail about electromagnetic induction. As the field becomes stronger or weaker, the number of magnetic field lines in the region enclosed by a loop of wire varies. This gives rise to the current in the loop even if the wire is not moving. I think this is actually kind of cool because the changing of magnetic fields creates electrical fields because electric fields exert a force on a charge whether it is moving or not in motion. Magnetic fields act only on moving charges, which is where our electrical generator comes in to play because a simple generator consists of a loop of wire that is made to rotate around two opposite magnetic poles. As the loop rotates, the current and potential difference, or voltage, is generated, varying in magnitude and alternating in direction. And this is what we call our AC, or our alternating current.